Okay, so that's your homework. We're now going to chapter 11, which is more derivatives, but now we're going to do derivatives of logs and exponents, which I'm sure thrills you really amazingly. Actually, they're not that hard. You might think that the derivatives would be difficult, but some of them are all very simple. We're going to start with the derivatives of natural log functions. What is a natural log? Well, if you take the log to the base e of y and make that equal x, I can convert that to an exponential. Remember? I can convert that to an exponential. That's why, and that would be y e to the x. The way I taught it in my class was cross out the log, bring the e up below the x, and have it push up the x. So you get y equal e to the x, which is called an exponential function. And these functions look something like this, depending upon, but most of the time they'll start at 1, they'll cross the, and they'll go like this. That's just a standard exponential function. Depends on what the constant is in front there. The usual way of writing an exponential function would be a e to the bx. Okay, and depending upon what the base is, that's what happens to this curve. Could be up or down, right to left. It could be skinnier, but we're not interested in that. What we're interested in is here is this just tells you that what is a log. Okay, if you look at x here, this is the result of solving the log of y. And you go down to the exponential, so the log, the value that comes out of a log is simply the power of the exponential. So a log is a power. All right, but now we want to do log functions. So let's write log to the base y in another way. And this is the standard way, anyway, it's in your calculator. Okay, log to the base ey is simply said as, log to the y. All right, this is equivalent. You see this, you see that. So we're going to be dealing with natural logs only. We're not going to do any other logs in this course because they get a little bit hairy. So what we want to do is take a few examples, and we're going to start with basically example 1. Before I give examples, I'm going to give a rule. I'm sorry. So this is rule for differentiating as I get below here, this shakes more. Natural log functions. So, example 1. Simple one. Well, let's give the rule first. I keep wanting to go to the example. The rule is a general rule. If y equals log of u, the natural log of u, then the derivative of y, with respect to x in this case, is going to be 1 over u du times du dx. This covers any where u is going to be a function of x. U could be any functional polynomial that you want. It could even be a log function. Those are all a little bit more difficult. So let's try to solve some problems. I did not go into log and details because you had covered this in QBUS-100. What we're interested in differentiating. So let's take a simple example, most basic, y equals log of x. Well, in this case, u equals x, du dx equals 1. So according to our rule, dy dx is going to be 1 over u, du dx, or 1 over x times 1, or simply 1 over x. That is the derivative of that function with respect to x, simply 1 over x. It does get more complicated, so let's take another example. Let's say y equals the log of 3x squared. Notice, what do we have here? We have the log, that u, which is always the argument inside the log. Everything that's in the parentheses after the log is always called the argument. It's a mathematical term. Obviously developed while the mathematician was talking to his wife. So dy dx is going to be 1 over u or his girlfriend, okay, or his mother. Okay, it's going to be 1 over 3x squared and times 6x. So that's 6x over 3x squared. 3 into 6 is 2. Okay, I can bring this up here, or I can bring this down here and make this a negative. So I'm going to get 2 divided by x. And that's my derivative of 3x squared. Okay, let's go and get a little bit more difficult now. And then we'll do some practical examples. Maybe not today, we'll see. So let's take another example. Okay, so this example is one that's a little bit more complex, where y is x third plus 3 the natural log of x squared. Notice this is not a log. In order to take the derivative, I have to take the derivative of each term. So I would take the derivative of this one. That's a simple power rule. I forgot to put the n. Okay, so this is easy. The derivative of this is 3x squared. That's a simple power rule. Now this is an x squared. So this says let u equal x squared. So du dx is 2x. That means that from our rule, dy dx is 1 over u du dx, or 1 over x squared times 2x. I can now add that to here. It's going to get 2x over x squared. Okay? This is going to be 3x squared plus 2 over x. Now, what happened to my 3? What happened to my 3? I forgot to include it, right? What do I do with my 3? Well, 3 is a constant. I can always bring that outside of the derivative. So here's what I'm going to do. Before I substitute in here, I'm going to bring the 3 out here. So I'm going to have 3 times whatever this derivative was. I can call that a. All right, so that'll give me the 3 outside here times 2 over x, which is going to be 3x squared plus 6 over x, and that's my answer. When you have a leading value, especially in the log and exponents, I advise that you take it outside of the derivative because it's multiplied. It's not going to change. And this way you can just work on the log function independently. We'll do another one like this just to clarify it. So anyway, this is your answer. Don't forget, it's in terms of x's. We had a log function, but our answer is in terms of x's. Okay. So let's see if we can do another one like this with a constant in front. And let's say we take another example, and just to show you how to do this, let's say y equals 15, the log of 4x to the third. Well, I want to take the derivative of y with respect to x. I'm going to take the 15 outside and just work on the log. I'm going to get u equals 4x to the third. How many minutes?
We got 2.5.
Okay. du dx is 12x squared. So that means all I have to do is substitute 15. Well, the derivative of this function we said is 1 over u du dx. So that's going to be 1 over 4x third times 12x squared. 4 goes into 12 3 times. I get 3x squared over x third, or 3 over x. So now I can substitute it back in here. dy dx is going to be 15 times the derivative of that, which is 3 over x. So we get 45 over x, and that's where the constant comes in since it doesn't change. It's a lot easier bringing those constants outside. Now, we are going to have homework on this, and a number of you don't have the book. So section 1.1 and 1.2, I'm going to scan and send them to you with the questions and the answers. Okay, so don't worry about that. Section 11.3 and the rest of the course will have a worksheet.